Welcome to Brain Vision.
Hi, everybody. So for this problem, we are told let the R be the value ionic separation of the R, which the U total or the potential total is a minimum, and use this differentiation to find an equation that relates to it. So it gives us a total here, and I'll explain what I'm going to be doing. This is a problem for one-dimensional calculation. That is what we're doing. And it looks like we're doing the potential energy of the kind of crystal from example 42.4. And let me just write everything out. And before I start solving, I'll explain it a little bit more what I plan to do, okay? It's just easier to write it out and then explain. A and the radius to the eighth. And they have it here. So what we'll be doing is expressing the total potential energy, V total, and we'll be taking the differential equation of the potential energy. Okay, and this is the potential energy here, okay? So we're going to be taking the differential of this. So for that, we're going to do dr, and you can use either V or U. I'm just going to use this U because that's what they had in the problem. And we're going to be differentiating this to find the V total. And for part B, I'll explain before I begin that what we'll be doing just to refresh your brain for part B. So take the differential of the R. So you're just going to use from here. And for that, we end up with 2e squared, because remember, we're just looking at just this r. We're not caring about anything else in here. 4 pi epsilon naught r squared minus a 8a. There we go, if I can learn to speak. And we're going to actually set this to 0. And so from here, what we're going to be doing is trying to solve for the r, okay? Oops, if I can do this. There we go. We'll just solve for this r. And because of that, let's just rewrite it so that way we can get all this kind of conjumbled together. So we have here that this, and I'm actually, let me just write this in a different color. So we have this, so we end up with not 2 up there. There we go. Just keep making mistakes. So we see that we want this to also have 2. So, and let's do this in green. So we're just going to multiply by green on both sides by 2. And because of that, we end up with so here we have 4 pi epsilon naught r to the 9th, because we also see that this has r to the 9th. So wait here, oops, we learn how to do math, guys. Here we need this, so we're just going to multiply it by 7, so it's just adding here. So we've r to the 9th over alpha e squared r7 minus 8 a 4 epsilon naught. Okay, and this thing is going to equal to 0. And you're just going to solve for r. And so your r is, let me scroll down. So we're going to scroll down for r. And we have 8a times 4 pi epsilon naught divided by alpha e squared to 1/7. Okay? And now we're going to substitute the values that we have. And we're just going to do this because we want to solve for. So we have 8a. Okay? And let's see if we did this correctly. Actually, let's do this a little bit slower. Okay. I prefer this in real time with everyone, so that way we're not doing anything crazy here. So we combined everything here together, and what we want is this R on the opposite side, but we just need to simplify this just a tad bit, at least on one of these sides. Okay. And this is not wrong, by the way. I'm just trying to see what we did here just to make sure that we have everything correct. Okay. And that's kind of important when you do this, is if you feel like something's off, just check it out, because sometimes it might be off. And that's what I was feeling a second ago. Okay. And we're going to substitute values here. So we have 8a. And here we have 9 times 10 to the 9th in m squared divided by c squared times 1.75. And also times 1.6 times 10 to the negative 19 c squared. The whole thing squared. And this is to the 1/7. Okay. And here we have 1.1 times 10 to the 4th, a to the 1/7. And so now we need to do this value of r for the twice the second integral, which is going to be greater than 0. And so now we have the r value. And what we can do here is, so we have this, okay? And the minimum here, what we end up having is we have this for the minimum V total is this 1.1 times 10 to the 4th, a to the 1/7. Okay, and but for the NaCl molecule, we have R equals 0.281 times 10 to the 9 meter. Okay, and because so for this, we can actually use this together and kind of make a oops. There we go. And for this, we have 0.281 times 10 to the negative 9 meters over 1.1 times 10 to the 4th. And we're just going to do to the 7th to cross that out. Or more importantly, if I just do that here, perfect. And we get 7.1 times 10 to negative 96. Okay, so now what we can do is go back up to our original. Okay, now we know all the values. So since we know all the values, what I'm going to rewrite down here is I'm just going to do one part at a time, and then we'll just add them together. And we have 4 pi epsilon naught r. And here we have 1.75. We have 1.6 times 10 to 19 C. 9 times 10, 8, oops, to the 9th. In m squared over c squared. Times 0.281 times 10 to negative 9 meters. And from here we get negative 8.97 EV. And now let's do the other side, which is just a over r to the 8th. We have 7.1 times 10 to negative 96. 0.281 times 10 to negative 9 meters to the 8th, and we get 1.14 eV. And so now we have the potential energy, and that is just going to be negative 8.97 plus 1.14, and of course we have the EV outside, and we get negative 7.83 EV. Okay? And now what we can do is for part B, which is not going to be that long. And let's just say it. So part B is the quantity of the negative U total potential energy is the energy required to remove the sodium ion with a chlorine ion from the crystal, forming a pair of neutral neutrons. Okay? To calculate the energy required to move the pair and experimental value for the quantity, how well does this calculation agree? Okay, so what we're going to be doing is just taking potential energies that we have for both the sodium plus, so we have it as 5.14, and the potential energy of this one is 3.61 EV. And then we're also taking this guy here. And what we're going to be doing is the energy required to separate the sodium atom and the chlorine atom from the nucleus of the crystal is we're just going to be adding all of them together. So we get 5.14 plus 3.61. And actually, we're going to be minusing this one, 7.83, because since it's positive, it's just going to be negative here. And we get 6.3 EV. And we're not quite done. And we're just going to find the percentage error. And we got 3.9 minus 6.3 divided by 6.39. And times 100. And we get 1.41% for the percent error. And that's the end of this question.